Section 1.7, Inverse Functions. Learning Objectives. In this section, you will 1. Verify inverse functions. 2. Determine the domain and range of an inverse function, and restrict the domain of a function to make it one-to-one. 3. Find or evaluate the inverse of a function. 4. Use the graph of a one-to-one function to graph its inverse function on the same axes. A reversible heat pump is a climate control system that is an air conditioner and a heater in a single device. Operated in one direction, it pumps heat out of a house to provide cooling. Operating in reverse, it pumps heat into the building from the outside, even in cool weather, to provide heating. As a heater, a heat pump is several times more efficient than conventional electrical resistance heating. If some physical machines can run in two directions, we might ask whether some of the function machines we have been studying can also run backwards. Figure 1 provides a visual representation of this question. In this section, we will consider the reverse nature of functions. Figure 1. Can a function machine operate in reverse? 1.7.1. Verifying that two functions are inverse functions. Suppose a fashion designer traveling to Milan for a fashion show wants to know what the temperature will be. He is not familiar with the Celsius scale. To get an idea of how temperature measurements are related, he asks his assistant, Betty, to convert 75 degrees Fahrenheit to degrees Celsius. She finds the formula. C equals 5/9 times, open parenthesis, F minus 32, closed parenthesis. And substitutes 75 for F to calculate. 5/9 times, open parenthesis, 75, minus 32, closed parenthesis, almost equal to 24 degrees C. Knowing that a comfortable 75 degrees Fahrenheit is about 24 degrees Celsius, he sends his assistant the week's weather forecast from Figure 2 for Milan, and asks her to convert all of the temperatures to degrees Fahrenheit. Figure 2. Monday, 26 degrees Celsius, 19 degrees Celsius. Tuesday, 29 degrees Celsius, 19 degrees Celsius. Wednesday, 30 degrees Celsius, 20 degrees Celsius. Thursday, 26 degrees Celsius, 18 degrees Celsius. At first, Betty considers using the formula she has already found to complete the conversions. After all, she knows her algebra, and can easily solve the equation for F after substituting a value for C. For example, to convert 26 degrees Celsius, she could write 26 equals 5/9 times, open parenthesis, F minus 32, closed parenthesis. 26.9 over 5 equals F minus 32. F equals 26.9 over 5 plus 32, almost equal to 79. After considering this option for a moment, however, she realizes that solving the equation for each of the temperatures will be awfully tedious. She realizes that since evaluation is easier than solving, it would be much more convenient to have a different formula, one that takes the Celsius temperature and outputs the Fahrenheit temperature. The formula for which Betty is searching corresponds to the idea of an inverse function, which is a function for which the input of the original function becomes the output of the inverse function and the output of the original function becomes the input of the inverse function. Given a function f of x, we represent its inverse as f-1 of x, read as f inverse of x. The raised -1 is part of the notation. It is not an exponent, it does not imply a power of -1. In other words, f-1 of x does not mean 1 over f of x, because 1 over f of x is the reciprocal of f, and not the inverse. The exponent-like notation comes from an analogy between function composition and multiplication. Just as a to the power of -1 dot a equals 1. 1 is the identity element for multiplication for any non-zero number, a. So, f inverse, composed with f, equals the identity function. That is, f inverse, composed with f at x, equals f inverse of x, equals f inverse of y, equals x. This holds for all x in the domain of f. Informally, this means that inverse functions undo each other. However, just as 0 does not have a reciprocal, some functions do not have inverses. Given a function f of x, we can verify whether some other function g of x is the inverse of f of x, by checking whether either g of f of x equals x, or f of g of x equals x is true. We can test whichever equation is more convenient to work with because they are logically equivalent, that is, if one is true, then so is the other. For example, y equals 4x, and y equals 1 over 4x are inverse functions. F inverse, composed with f at x, equals f inverse of 4x, equals 1 over 4 times, open parenthesis, 4x, closed parenthesis, equals x. And f, composed with f inverse at x, equals f of 1 over 4 x, equals 4 times, open parenthesis, 1 over 4 x, closed parenthesis, equals x. A few coordinate pairs from the graph of the function y equals 4x are negative 2, negative 8, 0, 0, and 2, 8. A few coordinate pairs from the graph of the function y equals 1 over 4x are negative 8, negative 2, 0, 0, 8, 2. If we interchange the input and output of each coordinate pair of a function, the interchanged coordinate pairs would appear on the graph of the inverse function. A inverse function. For any one-to-one function f of x equals y, a function f inverse of x is an inverse function of f, if f inverse of y equals x. This can also be written as f inverse times f of x equals x for all x in the domain of f. It also follows that f of f inverse of x equals x for all x in the domain of f inverse, if f inverse is the inverse of f. The notation f negative 1 is read f inverse. Like any other function, we can use any variable name as the input for f inverse, so we will often write f inverse of x, which we read as f inverse of x. Keep in mind that f inverse of x is not equal to 1 over f of x. And not all functions have inverses. Example 1. Identifying an inverse function for a given input-output pair. If for a particular one-to-one function f of 2 equals 4 and f of 5 equals 12, what are the corresponding input and output values for the inverse function? Solution. The inverse function reverses the input and output quantities, so if f of 2 equals 4, then f inverse of 4 equals 2. F of 5 equals 12, then f inverse of 12 equals 5. Alternatively, if we want to name the inverse function g, then g of 4 equals 2 and g of 12 equals 5. B. Analysis. Notice that if we show the coordinate pairs in a table form, the input and output are clearly reversed. See Table 1. Table 1. X, f of x. X, g of x. 2, 4. 4, 2. 5, 12. 12, 5. Try it number 1. Given that h inverse of 6 equals 2, what are the corresponding input and output values of the original function h? How to? Given two functions f of x and g of x, test whether the functions are inverses of each other. 1. Determine whether f of g of x equals x, or g of f of x equals x. 2. If both statements are true, then g equals f inverse, and f equals g inverse. If either statement is false, then both are false, and g is not equal to f inverse, and f is not equal to g inverse. Example 2. Testing inverse relationships algebraically. If f of x equals 1 over x plus 2 and g of x equals 1 over x minus 2, is g equals f inverse? Solution. G of fx equals 1 divided by, open parenthesis, 1 over x plus 2, closed parenthesis, minus 2 equals x plus 2 minus 2 equals x. So, g equals f inverse and f equals g inverse. This is enough to answer yes to the question, but we can also verify the other formula. F of g of x equals 1 divided by 1 over x minus 2 plus 2. X equals 1 divided by 1 over x equals x. C. Analysis. Notice the inverse operations are in reverse order of the operations from the original function. Try it number 2. If f of x equals x cubed minus 4 and g of x equals cube root of x minus 4, is g equals f inverse? Example 3. Determining inverse relationships for power functions. If f of x equals x cubed, the cube function, and g of x equals 1 over 3, x is g equals f inverse? Solution. F of g of x equals x cubed over 27 is not equal to x. No, the functions are not inverses. D. Analysis. The correct inverse to the cube is, of course, the cube root of x equals x to the power of 1 over 3, that is, the 1/3 is an exponent, not a multiplier. Try it number 3. If f of x equals, open parenthesis, x minus 1, closed parenthesis, all cubed, and g of x equals cube root of x plus 1, is g equals f inverse? 1.7.2. Finding domain and range of inverse functions. The outputs of the function f are the inputs to f inverse, so the range of f is also the domain of f inverse. Likewise, because the inputs to f are the outputs of f inverse, the domain of f is the range of f inverse. We can visualize the situation as in Figure 3. Figure 3. F of x. Domain of f, a. Range of f, b. F inverse of x. Domain of f inverse, a. Range of f inverse, b. Figure 3. Domain and range of a function and its inverse. When a function has no inverse function, it is possible to create a new function where that new function on a limited domain does have an inverse function. For example, the inverse of f of x equals square root of x is f inverse of x equals x squared. Because a square undoes a square root, but the square is only the inverse of the square root on the domain, open square bracket, 0, infinity, closed parenthesis, since that is the range of f of x equals square root of x. We can look at this problem from the other side, starting with the square, toolkit quadratic, function f of x equals x squared. If we want to construct an inverse to this function, we run into a problem, because for every given output of the quadratic function, there are two corresponding inputs, except when the input is 0. For example, the output 9 from the quadratic function corresponds to the inputs 3 and -3. But an output from a function is an input to its inverse. If this inverse input corresponds to more than one inverse output of the original function, then the inverse is not a function at all. To put it differently, the quadratic function is not a one-to-one function. It fails the horizontal line test, so it does not have an inverse function. In order for a function to have an inverse, it must be a one-to-one function. In many cases, if a function is not one-to-one, we can still restrict the function to a part of its domain on which it is one-to-one. For example, we can make a restricted version of the square function f of x equals x squared, with its domain limited to, open square bracket, 0, infinity, closed parenthesis, which is a one-to-one function. It passes the horizontal line test, and which has an inverse, the square root function. If f of x equals, open parenthesis, x, minus 1, closed parenthesis, all squared, on, open square bracket, 1, infinity, closed parenthesis, then the inverse function is f inverse of x, equals, square root of x, plus 1. 1. The domain of f, equals, range of f inverse, equals, open square bracket, 1, infinity, closed parenthesis. 2. The domain of f inverse, equals, range of f, equals, open square bracket, 0, infinity, closed parenthesis. Q&A. Is it possible for a function to have more than one inverse? No. If two supposedly different functions, say, g and h, both meet the definition of being inverses of another function f, then you can prove that g equals h. We have just seen that some functions only have inverses if we restrict the domain of the original function. In these cases, there may be more than one way to restrict the domain, leading to different inverses. However, on any one domain, the original function still has only one unique inverse. A. Domain and range of inverse functions. The range of a function f of x is the domain of the inverse function f inverse of x. The domain of f of x is the range of f inverse of x. How to? Given a function, find the domain and range of its inverse. 1. If the function is 1 to 1, write the range of the original function as the domain of the inverse, and write the domain of the original function as the range of the inverse. 2. If the domain of the original function needs to be restricted to make it 1 to 1, then this restricted domain becomes the range of the inverse function. Example 4. Finding the inverses of toolkit functions. Identify which of the toolkit functions besides the quadratic function are not 1 to 1, and find a restricted domain on which each function is 1 to 1, if any. The toolkit functions are reviewed in Table 2. We restrict the domain in such a fashion that the function assumes all y values exactly once. Table 2. 1. Constant. F of x equals c. 2. Identity. F of x equals x. 3. Quadratic. F of x equals x squared. 4. Cubic. F of x equals x cubed. 5. Reciprocal. F of x equals 1 over x. 6. Reciprocal squared. F of x equals 1 over x squared. 7. Cube root. F of x equals cube root of x. 8. Square root. F of x equals square root of x. 9. Absolute value. F of x equals the absolute value of x. Solution. The constant function is not 1 to 1, and there is no domain, except a single point, on which it could be 1 to 1, so the constant function has no meaningful inverse. The absolute value function can be restricted to the domain, open square bracket, 0, infinity, closed parenthesis, where it is equal to the identity function. The reciprocal squared function can be restricted to the domain, open parenthesis, 0, infinity, closed parenthesis. B. Analysis. We can see that these functions, if unrestricted, are not 1 to 1 by looking at their graphs, shown in Figure 4. They both would fail the horizontal line test. However, if a function is restricted to a certain domain so that it passes the horizontal line test, then in that restricted domain, it can have an inverse. Figure 4. A. Absolute value. B. Reciprocal squared. Try it number 4. The domain of function f is, open parenthesis, 1, infinity, closed parenthesis, and the range of function f is, open parenthesis, negative infinity, negative 2, closed parenthesis. Find the domain and range of the inverse function.